a certain violin string, the A below middle C, flute, to that produced by a tuba. Suppose the note middle C has a frequency of 256 Hz. A student uses an oscilloscope Question 6. A certain violin string vibrates back and forth at 640 times a second. What is the frequency of the sound that it produces? Now remember, the frequency of a sound wave is determined by its source. In this case, that source is a vibrating violin string. If the violin string vibrates at 640 Hz, that is 640 times per second, then the sound wave it produces will be 640 Hz. So even before we go that far, we can see right away that it's not going to be either of the bottom two, because those aren't measurements of frequencies, they're measurements of periods, because they're given in milliseconds. So our only correct answer has to be something in Hertz, and as we saw, if the violin string is vibrating 640 times a second, that is 640 Hz, then it will create a sound wave with 640 Hz as its frequency. Question 7. The A below middle C has a frequency of 220 Hz. What is this musical note's period? If we have a wave of any sort, sound wave or not, we can find its period if we know its frequency. So what's the formula again? That's right, the period equals 1 divided by the frequency. So that will tell us pretty easily that period of this musical note, the A below middle C, is going to be 1 on F, or 4.5 milliseconds. Question 8. In terms of frequency, compare the music produced by a flute to that produced by a tuba. Now, assuming that we have a cursory knowledge of musical instruments, we know that flutes tend to produce quite high notes, whereas tubas produce very low notes. So, how will that change the frequency? Well, if we have very high notes and very high pitches, that means we have high frequency, and if we have very low notes and very low pitches, that means that we have very low frequency. So what's our answer? Well, the flute produces music with a much higher pitch than music produced by a tuba, which means that the flute, which has a higher pitch, also have a higher frequency than the tuba, which has a lower pitch and a lower frequency. Question 9. Suppose the note middle C has a frequency of 256 Hz. This isn't exactly accurate, but it's accurate enough for our purposes. Calculate the frequency of the C that is 1 octave above middle C. So how is this going to change? Well, we know that 1 octave corresponds to a doubling of the frequency. We know that the frequency of our starting note, middle C, is 256 Hz, so to move 1 octave up, we just double it. 256 times 2 is 512 Hz. So that means that the difference between these two notes, the distance between middle C and the C above, is 256 Hz. So there are 256 Hz in between these two notes. Part B. Calculate the frequency of the C that is 2 octaves above middle C. At first we might think, well, there are 256 between these first two Cs, so surely there's going to be 256 Hz between these next two Cs. But that's not quite right. If we move up 256 Hz from this C, we'll actually end up at the musical note G, which is halfway in between two Cs if we look at the frequency. So in fact what we need to do is we need to move up 1 octave from here, and when we move up an octave, we double the frequency. So 512 Hz times 2 is 1024 Hz. If we were to add 512 to 256, which is the interval between these two Cs, then we would not in fact get the next C. We would get one of the harmonic series, or one of the elements of the harmonic series. But that's more sort of advanced acoustics, so I'll leave it here for now. Finally, question 10. A student uses an oscilloscope, which of course is a device for measuring the wavelength or frequency of waves, to measure the wavelength of two musical notes in the same medium. So they're not traveling at different speeds and we don't need to worry about what they're traveling through. If two notes are 1 octave apart, how will their wavelengths differ? Now this is an interesting question, isn't it? If we're trying to relate frequency and wavelength, what equations do we know to do that? Well, there's one that we keep coming back to, is V equals F lambda. And in fact, we can use that here as well. If the two sound waves are both traveling in the same medium, that means that V is going to be a constant number. So that means that frequency times wavelength for the first wave will equal the frequency times wavelength for the second wave, right? So, if the two notes are 1 octave apart, how will that change their wavelengths? Well, we know that a difference of 1 octave corresponds to a frequency doubling, or halving if we're going back the other way. And so if F1, for example, is double F2, but we know that this condition has to hold true, then we can see that lambda 1 will need to be half of lambda 2 in order to keep the equation correct. So, if the two waves travel through the same medium, they'll have the same velocity. That's an important part of the question, because if they're traveling through different media, then their wavelengths will depend on the speed of sound in that medium. So, from our equation, V equals F lambda, that means that the higher note, the note that is 1 octave above the other, will have a shorter wavelength by a factor of exactly 1/2. So that's the end of the questions. That means we finished talking about the different frequencies of different notes, in particular how those frequencies sound when we're listening to things like music. We've also talked about the difference between very, very high pitches, that is ultrasound, and very, very low pitches, that is infrasound. We can't hear these, of course, but that doesn't mean they're not sound waves. In the next section, we'll be looking at the energy transmitted by waves, and in particular, the amplitude and loudness of sound.